Zipf's law, it's basically based on the observation that in any text you have, in any language, some words are going to be a lot more frequent than others. So in English, in a random piece of English text, words of and the are going to make up about 10% of all word occurrences, and a word like aardvark is extremely rare, right? So if you're reading a randomly picked chunk of English, it's very, very likely that you will see the words of and the, and it's extremely unlikely that you'll see the word aardvark. So no surprise there. But interesting things happen if we actually rank the words by frequency with which they occur in the text, right? So this is a bunch of words from an Associated Press newswire. And if you count how many times you see every single word in this corpus and you rank them by decreasing order of frequency, you get something. You get an interesting observation, right? So the words that occur in the beginning, that's not surprising, right? The is the most common, of is the most common. But if you look at the frequencies and you look at the ranks, you might notice an interesting pattern between them, right? So if I take the frequency and multiply it by the rank, I get roughly the same number for every word. Not the same, they will vary quite a bit, but they are numbers in the same ballpark, right? So for the, I have 2.5 million times 1, that's 2.5 million. So of, I have 1 million times 2, that's 2 million. Pretty close. 2, I have 900 times 3, that's going to be 2.7 million. Not very far off, right? 89. Okay, let's pick that word. So 350,000 times 9. So that's actually going to be over 3 million, but still roughly in the same ballpark of 2 to 3 million. So that's an interesting observation, and that is something known by the name Zipf's law. And Zipf's law, it's an empirical law. It's a law based on observation. And the law says that if you rank the words in decreasing order of frequency, then rank multiplied by the frequency of the word is going to be approximately a constant. Okay, so it's a pretty powerful law. It's not entirely clear how it arises, but what's neat about it is you can observe it in just about any collection of text. So this was Associated Press, and it's actually really easy to reproduce this result for just about any corpus that you might want to work with. So let's see. Right here, I have the text of the English Bible. Right. So if we do the same thing with the English Bible, any guesses what's going to be the most frequent word? God. That's what I thought. It should be God. So let's see if it actually is, right? So so that's the Bible, right? Well, the beginning of it. So what I'm going to do is I'm going to play with it just a little bit using some basic shell tools, and that's something that I would encourage you to do on your own. Right? Just because it's easy and it's fun and you get a lot out of it, right? So for now, I'm just going to take the first 20 lines of the Bible. The first thing that I'm going to do is I'd like to lowercase all the words, right? Just so that I don't count uppercases and lowercases differently. So so I'm going to take any uppercase letter and replace it with a lowercase letter. So TR is a little... you probably can't see that. TR is a little Unix utility that allows you to replace any character with any other character or sort of a range of characters with other characters. Right. So I do that, and yay, I've what's it? Oh yes, that's right. Thank you. Okay, so that lowercase them all. And now what I'm going to do is I want to split it up into individual words. And the simplest way to do that for the Bible is to take anything that is not a letter and replace it with a new line. Right? Then I'll have every single word on a separate line. So that's what I'm going to do again. I'm going to say a complement of A to Z. So anything that is not an A. Anything that is not a lowercase letter is going to go to a new line. Right. So, and that's what I get. I also have lots of blank lines, but they're not gonna affect anything. So now what I'm gonna do is I'm gonna sort these things, right? And if I sort them, sure enough, that's what I get. And yes, you're right. There's a bunch of God in there. And the next thing that I will do is I will count. So in the sorted list, I'm going to collapse all the repeated lines using this little Unix utility called unique. Right, so I'm going to say unique -c, and that's going to collapse them all and count how many times I've seen them. Right. So if I do that, I get something like that, and then I'd like to sort them in reverse order by the frequency that I got. Yay. Okay. So that's the head of the first 20 lines of the Bible. And the most frequent word is actually not God. It's the, just like the rest of English. Now, God is pretty frequent. And if you compared it to a scientific literature, it would be a huge difference. But English is English, and the is going to be the most frequent word, regardless of what you're dealing with. So that's the first 20 lines. Now let's, the beauty of this is, well, now let's take the entire Bible. Right, so I'm just going to cat the entire text file, and it's going to take a little bit longer, but not as long as you would expect. Okay, there you go. So and you see, God's actually moved down quite a bit. I don't think God is in this list anymore. Well, God. But the beginning of the list is very much the same. So you have the and of. And if you look at it roughly, so ignore the first line. The second line, the, has about 7,500 occurrences. So and actually has about the same as the. So Zipf's law breaks right there. But off is back to the right scale, and he is back to the right range, and so on and so forth. Right. So just by looking at this, you see that okay, it held on Newswire. It also holds in the Bible, and any collection of English text that you take, if you do the same procedure, you're going to see the same picture. You're going to see that rank times the frequency gives you approximately the same number for lots and lots of different words. So if you plot it graphically, this is what it looks like. So that's our Associated Press corpus. And I'm plotting rank on the x-axis and probability, which is frequency divided by the total number of tokens, on the y-axis. Now, it actually looks a little strange. That's because I'm plotting it on a log-log scale. Right? Why am I doing that? What if I didn't do log-log scale? What if I plotted on a linear scale? You wouldn't see anything. Right? Because the plot of 1 over x looks like that. It'll hug the axis, so you wouldn't be able to see anything. So it's a convention to plot these things on a log-log scale. So the black points here are the observations. These are the actual frequencies of the words in the Newswire, and the blue line is what you get by Zipf's law. Right? So that's if you say that the frequency is approximately that constant divided by rank, that gives you a straight line in log-log space. It's just 1 over x, by the way. Now, the neat thing, as I said, is this is going to hold for just about any data set of English, and surprisingly, the same result holds for just about any other human language on Earth, and lots of non-human languages as well. So lots of synthetic languages have the same property, and lots of data sets that are not text have the same property, which is kind of interesting. So here's an example of Zipf's law in a domain which has nothing to do with text. So these are the largest cities in the United States as of a year ago, and this column is their population estimate from a census, and that is the rank. And if you look at the numbers, you'll see Zipf's law again, right? So New York City, the population of 8.5 million, LA comes second with 3.8, 3.8 times 2, it's a little bit under 8, right? Now Chicago, 2.7 times 3, so that's going to get you to, what's 8.1, so surprisingly close. San Jose, number 10, 900 times 10, you get 9 million. right? So there you have Zipf's law, again, a domain that has nothing to do with text, but you're seeing Zipf's law again. So you have to be cautious. This is not universal. So if you try to do this, for example, with cities in China, it wouldn't work. Curious observation, nobody knows why, but that's true.